Kia ora, Year 11 and 12. This is the first video I'm making on improper integrals. So this is revision if you are in 13 MCA for the A-level Pure 3 exam, and it's new content if you're in the AS class for the Pure 1 exam. It's not covered in Level 3 NCEA, but some of the ideas in this video and the next one about limits are quite useful if you're doing scholarship calculus. Okay, so we're going to start off by just thinking about what it means to find the area under a curve. We're going to start off with an easy case that we're used to, where we've got finite limits of integration and where we've got no issues with the function being defined anywhere between the two endpoints. So the way we write that is like this. So b and a are the limits of integration, and f of x is the function we're going to integrate. So the example I'm going to work with in most of this video is the function 1 over root x. And it's often useful to write that as x to the negative a half. Okay, we're going to find the area under that curve between x equals 25 and x equals 9. So let's do that now. So you should pause the video and do this yourself, and then check that you've got the same steps as me. The first thing I'm going to do is rewrite it as x to the negative a half. And then I'm going to integrate it. So this is going to go to x to the power of 1/2. I'm leaving a gap here because I need to have a coefficient that gets me back to an invisible 1 here. Right? Now, if you're watching this video, hopefully that all feels very, very familiar. So what I need to have here is 2, right? Because when I differentiate this, I'll get 2 times 1/2 gets me back to 1. Let's just get rid of all of the silly underlines there. Okay, so we're up to here, and we're going to evaluate that at my 2 limits of integration. And there's nothing bad going on at all. So here we've got 2 root 25 minus 2 root 9, which is 2 times 5 minus 2 times 3, which gives me 4. So that's saying that the area under the curve is 4. Now, you're probably watching going, oh, why is she going so slowly? Well, I'm going slowly because it's about to get a little bit weirder. But this is the first one we've got. So there's my function, 1 over root x. And you can see that here, we've just got a scale here that's going out in 2s. And we're interested in the area between 9 and 25. So that's that shaded area there. The function is continuous between 9 and 25, and the function is defined at these 2 endpoints. But you can see in here there are going to be 2 places where interesting things happen. And the first one is that x is not defined at 0. So 1 over root 0 is undefined. And then the other interesting thing that's happening is that obviously we've got a horizontal asymptote out here. So as x gets bigger and bigger, what's going on with the area under the curve there? So in this example, one of those is going to be a well-defined number, and one is going to be undefined. But it's a little bit weird to think about what we mean by the area under the curve between, say, 25 and 0, because we don't have a value at 0. Right? So what's happening with this curve here is it's getting closer and closer to 0 as x can get closer and closer to 0, and y is getting bigger and bigger. But it turns out that it does make sense to think about the area under the curve between the values 25 and 0. So in this case, we're going to find that the integral does exist. Sometimes you'll see that as the integral has a finite value, or the integral converges. They're basically similar ways to say the same thing. But let's start off by just looking to see what happens as we get closer and closer to the lower limit being 0. So we'll start off with the lower limit being 1. And we've already done this work. So that gives me, again, this. And when you evaluate that at those 2 limits, you get 2 5s minus 2 1s. So that gives me 8. So that's the first integral there. So that's between 25 and 1. Now, when we move down to here, this is the integral that we get when we've got the integral between 25 and 1/10, or 0.1. and that works out to be 9.368. So you can see that the area is growing, but the question is, how fast is it growing? Is it growing so fast that there's no number that we're converging to? So you might want to pause the video here and just try a couple more out and see where it's heading to. I've got some graphs drawn to show you that. Now in the next one, it's getting really hard to see that we're getting very close to zero. In this next one, I've changed the scale so that you can see the gap in here. So this one is the integral between 25, so the area under the curve between 25 all the way out there, and 100, so 0.01. And this one works out to be 9.8. So you probably are thinking, I wonder if this is going to head towards 10. So I haven't done any more, but you might want to just try and figure out, just do one last one on your calculator, because I want you to have some intuition for what's going on with this. So do, how many zeros have I done? 7 zeros and then a 1 of that function. And you should see that we're getting very, very close towards 10. So 9.9998. Right, but how do we do this without doing weird arbitrary numbers that are just above 0? Well, what we're going to do is we're going to look at an integral where we've got a discontinuity at one of the endpoints. And we're going to define this integral as follows. We're going to say, let's think about getting very, very close to 0 from above. And let's take the limit as that lower number gets very, very close to 0 from above. So for some of you watching this, it might be the first time you've seen this limit notation. Lim means limit, and this is saying as a gets very close to 0, and the little plus means from above, right? And that's exactly what we were doing up here. Whoops, wrong one. Up here, right? So we were getting very, very close to 0 from above, but we're doing this now with a little bit more theory, but not much more. So that's how we define that integral. So we're just going to work with this thing here, which is easy, right? There's nothing bad about this. My lower limit is just a instead of the very difficult 0. So we work this through and we just let that limit sit there. And this is how we're going to do all of our indefinite integrals. So we take the limit as a is going to 0, and we know what this thing here is. It's going to be 2x to the 1/2 evaluated at 25 and a. So just don't worry about that limit stuff there yet. We'll get to that in a second. So again, we've got 2 root 25, which gives me 2 5s are 10. Take away 2 root a. Okay, now we look and we say, well, what's happening to all of those bits as a goes to 0? A goes to 0 from above. Well, nothing happens to the 10. It's not affected by the a, so it's just 10. And then what about this? Well, as a is going to 0 from above, the square root of a is going to 0 from above as well. So it'll be a tiny positive number. And then we're timesing that by 2, so we've still got a tiny positive number. So the limit of 2 root a is 0. Okay, so you can see that the limit part here has fallen away because the limit of 2 root a is 0. So my answer is 10, and that's my integral, right? So it's finite, it has converged, if you want to say that. Well, it's kind of weird to say that, but it's finite, and the limit exists, and the integral exists. Okay, so I'm already at 9 minutes to do one. What we're going to look at now is one at the other end, where we're looking at what happens when we want to find the area going off to infinity. So on this graph, what we're now interested in is the area from 25. Oh, I can't do that. I've got to do my colouring in properly here. Right, so we now want to see if that curve goes out to infinity here, what's the area under the curve but above the x-axis there. Now again, this feels kind of weird to think about, right? Because obviously we're saying, well, what do you mean? Because we're going on forever and ever out here, right? We're getting bigger and bigger. So it's kind of a tipped upside down version of what we meant by talking about the area under the curve going all the way back to 0. The difference is in this case, And for this example, and not for lots, the integral here is not going to exist. Okay, so let's look at how we write it. We want to find the area under the curve between infinity and 1 over root x dx. So rewriting that straight away as a fractional power, we get this again. So we are going to define this integral as follows. Pen's doing a weird thing. So we'll define the integral between infinity and a of f of x dx as the limit of my top limit of integration, b, getting bigger and bigger. So we've said that this is what an integral going on to infinity is. So we're going to do exactly what we did before, but it's going to work out a bit differently in this case. So here we've got this, the limit between infinity and 25 of x to the negative a half dx. So that's equal to the limit as b goes to infinity of this. And again, just don't worry about that limit operator, right? That's going to work like this. So we've got 2 times x to the 1/2 evaluated at b and 25. Right, so as b gets very, very big, what's going to happen? Well, here we've got 2 root b minus 2 root 25, so minus 10. But this time it doesn't work out as nicely, right? Because as b gets bigger and bigger, the square root of b also gets bigger and bigger, and that also goes to infinity. Okay, so if you think about taking the square root of 1 million, you'll get, what will you get? 1,000, right? If you think about taking the square root of 10 to the power of 24, you're going to get 10 to the power of 12, right? That is not stopping. The limit here is still going to be infinity, right? So we're going to write that down in some words. So as b goes to infinity, 2 root b also goes to infinity. So there's no finite limit. The integral doesn't exist. It's a very messy, long way to say all of that. The integral does not exist. Right, so you can see that if we go back, all the way back to that graph, this is saying that there is no value, right? Like here, the integral going back towards 0 was 10. But here, if you do the integral between 25,000 and 25 f of x, you'll get one number, right? Then if you change that and do 75,000, you'll get a bigger number, and so on. And no matter how much bigger you make the number, the area under the curve is not going to be getting closer to a limiting value. So this video is really, really long, and I know that when I make them 13 minutes long, I have about one person watching by the end. So if you are that person watching at the end, I promise you there will be a fruit burst when we get back to school, but you have to come and claim it. I'm going to do a couple more videos on this topic. One tomorrow with more practice with the limit being infinity, because I think that's what people find the weirdest, and then some that are quite similar to some old exam questions. So just leave me a comment if you've got any questions so far.